education.
Professores que
Analisa deles.
Okay.
Isso,
Our reports. Let's see. Some of you have already picked up your quizzes, some haven't, so let's make those back. I'll say a word or two about the quiz in just a minute, but let me also hand back the problem set.
So I'll do that.
Okay, all the solutions have been posted on Blackboard, i.e. the solution for the quiz and the solution for the second problem set. Okay? So what you want to do is take some time, it's good study time, to go and take your work and cross-check it with the solution. And think about, if there were some places where you lost some points, think about what you need to rethink. Okay? This is one way we learn. It's actually a very important way we learn. We make a mistake, we think about it, and what did I do wrong? Incorrect. Okay? So that is definitely an important part of the process, and I urge you to do that. Okay? And you're also welcome to bring your work in to me, and we can talk about any questions you might have. Okay? So, I strongly urge you to do that. Take a little time and think about it. With regard to the quiz, I'll make just a few comments about it in terms of, some of the key ideas that were involved. This was a situation where we had our gas in the cylinder with the movable piston, kind of our standard apparatus. We're given an initial volume and an initial pressure in non-SI units. So we've got to deal with units too. Okay? And we're told that the gas will expand to a given final volume. We're not told directly what the final pressure will be, but we're told that the pressure rises in direct proportion to the volume. That means the pressure is always proportional to the volume. That means the pressure can be equal to some proportionality constant times the volume, so that if you were to make a PV diagram, which is the first thing you have to do, you need to draw a linear graph. The pressure is linearly proportional to the volume. And you've got to figure out that proportionality constant. Okay? And then part 2 asks you to calculate the work done on the gas during this expansion. You can either do it by integrating negative integral PdV. Since the pressure is a linear function of the volume, the pressure is equal to a constant times the volume. You can figure out the constant from the information given, and you can integrate it. You'll get negative C V squared over 2 between V initial and V final. Or you can just find the area under the graph. Right? Either way, you just got to make sure that everything's in proper SI units when you do it. Okay? And then you will get the correct expression for the work done. And that's problem 1 and 2. Problem 3, I asked you to state the equal partition theorem in a simple, clear sentence. So I was basically looking for the fact that, the statement that, for every degree of freedom of a system, we should say quadratic degree of freedom, of a system in thermal equilibrium, you get an average energy of 1/2 times the Boltzmann's constant times temperature. Okay? Then use the equipartition theorem in problem 4, part 4, along with the ideal gas law to find the internal energy change, delta U, of the gas. So equipartition tells you that delta U will be the number of degrees of freedom over 2 times the number of molecules times Boltzmann's constant times the temperature change. It's delta U, so it's a delta T. You have to know that, that the gas, which is helium, you have to know that helium is monatomic, so the number of degrees of freedom F is 3 for each atom. So that you know delta U is 3/2 capital N KB delta T. But then you've got to use the ideal gas law to write N KB delta T in terms of things you know, which are pressures and volumes. So you can end up getting the following expression. The change in the internal energy is 3/2 times, parentheses, P final times V final minus P initial times V initial. That was just using the ideal gas law. And then you can calculate delta U in joules. Then I asked you to write down the first law of thermodynamics using mathematical symbols, and then to state what each symbol represents. So the first law says, in symbols, delta U equals Q plus W on. And stating what those are, you must say that delta U is the change in the internal energy. It is incorrect to just say it's internal energy. It is the change in the internal energy. Q is the energy transferred as heat, and W is the energy transferred as work. Okay? Then use the first law of thermodynamics to find the energy transferred as heat, Q. And tell me whether or not the energy is being added as heat or removed. So then you take the first law, solve it for Q, so Q equals delta U minus W on. Plug in your answers for delta U and W on. Remembering that the W on, by the way, that you get is a negative value. So you end up with a rather large positive value in joules for the energy transferred as heat. And since it's positive, you know the energy is transferred into the gas as heat. Then there was a bonus question, determine the molar specific heat capacity for the helium for this process. And you can do that basically by definition. The molar specific heat capacity is the heat capacity per number of moles. So you take the heat capacity, symbol capital C, and divide it by the number of moles of gas that you have. You cannot, unfortunately, just go to one of our canned equations for the ideal gas, like the molar specific heat at constant volume, because the volume of the gas isn't constant. That we had a nice simple canned formula for. It's the number of degrees of freedom F over 2 times R. Well, unfortunately, the volume isn't constant. Nor can you use the other canned formula we have for the ideal gas, the molar specific heat at constant pressure, because the pressure is not constant either. But you can go back to basic ideas and say the molar specific heat capacity is the heat capacity divided by the number of moles. Heat capacity, by definition, is the energy transferred as heat, Q, divided by the temperature change, delta T. So what you have to figure out is that the C molar is Q over N delta T. And then you've got to figure out, using what we've already talked about in other parts of this problem, how to write that in terms of things you know values for. So you can end up getting an expression that looks like this. C molar is 3/2 times R. That would be what you'd have for a constant volume process. Times the ratio Q over delta U. And you know the value of Q, and you know the value of delta U. And actually you can end up showing that that boils down to, it simplifies, because Q over delta U turns out to be 4/3. That C molar for this process is 2R. So you can study the solution for that to see how you could do that. But what you've got to make sure you don't do is just go to like C molar at constant volume or C molar at constant pressure, because neither of those is constant here. Okay, so that's our first quiz. We'll do another one a week from Thursday. Okay? And it will be about Chapter 2 material. And you've got your current problem set that you're working on for this week. Right? So we'll just keep going. Okay? Any questions about anything I've said? Okay, so we started chapter 2 in class on Thursday, and we're building towards stating the second law of thermodynamics from a statistical mechanics perspective, by the way. And we started by talking about concepts of microstate and macrostate for any given system. And so, to remind us, a microstate is when you take a system and you give a detailed description of what's going on at a very fine-tuned microscopic level. And a macrostate is where you kind of back off and you say, look, I don't need to know all those many fine-tuned details. I just need to know kind of on a bigger picture what's going on. Okay? Now, that's a little bit of just a description of microstate and macrostate, so we had to start getting more specific. So we took a specific physical system. We took what's called the two-state paramagnet. Okay? That consists of a sample. Let's say it's a chunk of some kind of solid. And inside that solid, there are a whole bunch, capital N, atoms. And on every atom, you boil that atom down to an object with a spin quantum number of 1/2. Right? So every atom has a spin quantum number of 1/2. That means if you take one of the components of the spin angular momentum, say the z component, there are only two possible values for s sub z. Plus h bar over 2 and minus h bar over 2. Everybody remember h bar means Planck's constant h divided by 2 pi. Now you put this object in an external magnetic field. We'll take the magnetic field to be in the plus z direction. And then you have a magnetic energy for each one of these atoms, where each atom, because of its spin angular momentum, has a magnetic dipole moment, mu. And the magnetic energy of each atom is negative mu dot b. And then what we said is this: a microstate of such a system would be to go down the line, every atom, all capital N of them, one by one, and keeping track of whether each magnetic dipole moment is up, i.e. along the direction of the magnetic field that's being applied, or down, opposite to the direction of the magnetic field. And that you only got two options for the magnetic dipole moment, up or down. Okay? So a microstate is a particular configuration where you go down the line of n atoms and you keep track one by one whether its dipole is up or down. Okay? That's a detailed description. And that's a microstate. A macrostate is to step back from that and say, look, I don't need all that detail. I don't need to know if particularly atom 1 is dipole up or down, and atom 2, and atom 3, and atom 4. Just tell me total. How many atoms have dipole up, and how many have dipole down? Without telling me which particular one is which. Okay? And one of the reasons why I only need to know it on that level of detail is that's all you need to know to calculate the total energy. How many dipoles are up, and how many dipoles are down. And that's a macrostate, where I just tell you, got so many dipoles up and so many dipoles down. Now the minute we were specific, microstates and macrostates with such a system, then we introduced the idea of multiplicity. Who can tell me what multiplicity is? I've gotten your brains warmed up, hopefully, reminding you what we've talked about. What is multiplicity?
The number of microstates for the particular numbers.
Correct. We discovered the macrostate idea being more big picture. There can be a lot of microstates for a particular macrostate. Okay? If I have 100 atoms, and I'm telling you that I'm interested in the macrostate in which there are 50 dipoles up and 50 dipoles down, then you could go down and figure out a lot of microstates that would correspond to that. 50 dipoles up and 50 dipoles down. A lot of different microstates that correspond to that one macrostate. So the multiplicity is the number of microstates that correspond to a particular macrostate. And one of the things we're going to discover as we go deeper into chapter 2 is that the multiplicity is going to be really important. Okay? And that in general, there are going to be some macrostates in which the multiplicity is absolutely humongous. Okay. I think that's where I left off. And I also think I mentioned that the next thing I wanted to do was show you another example of an actual physical system where we can do the counting of the microstates and the macrostates, the labeling, and figure out a formula for calculating the multiplicity of a macrostate. So the second example that I want to give, so this will be subsection B, is the case of what are called lattice vibrations in a solid. This is, in fact, what is called the Einstein model of lattice vibrations in a solid. A little later on in the semester, we'll learn a slightly more sophisticated model for lattice vibrations in a solid, but we'll start with this one. So what we're talking about are what are called crystalline solids. In a crystalline or crystalline, it's here pronounced both ways, solid, if you look in at the atomic level, you find that the atoms are in a very particular lattice structure with a very particular geometry, such as at the corners of a cube, that is just repeated over and over and over again. Okay? That's what we mean by a crystalline solid. And in a crystalline solid, you have a huge number of oscillating atoms in a lattice. For example, if you have a sample of iron, then you can look in, if you can look in and see the individual atoms, iron atoms, you will find that there are atoms at the corners of a cube with one other atom positioned at the very center of the cube. Each one of those represents an iron atom, and this whole structure is repeated in all directions. X, Y, and Z. Okay? And this is what's called a unit cell of the iron atoms, because this is the smallest structure that can be used to then repeat and construct the whole sample. Okay? And each one of these represents an iron atom, and I'll draw the little symbols here to represent oscillations. Each atom is oscillating about its own equilibrium position. Okay? And the bonds between neighboring ones, like this line represents, have some effective spring constant, I'll call K sub S. And of course each atom has some mass m. And what you can do is you can treat each atom as 3 independent, one-dimensional harmonic oscillators. Every atom can be treated as 3 independent, one-dimensional harmonic oscillators. It should seem somewhat reasonable that there would be 3 I can treat each atom as being 3 oscillators because there are 3 spatial dimensions in the lattice. Okay? The fact that they're independent of each other isn't necessarily obvious, but if you took classical mechanics, we studied what were called normal mode oscillations with systems of coupled oscillators, and we showed there where, as long as they're linear oscillators, each of these spring forces obeys Hooke's law, you can end up solving for a set of decoupled, independent, what are called normal modes. Okay? So you can show that every atom can be treated as three independent, one-dimensional harmonic oscillators. And what Einstein did is that he assumed that all of these harmonic oscillators have the same natural frequency. Okay? That turns out to be overly simplistic, which we'll learn later this semester how to do a better job of that. But this is a good starting point. Okay? So all these oscillators have the same natural frequency, F, which is, of course, 1 over 2 pi, the square root of the effective spring constant, K sub s, over the mass of an atom. Okay, notice then that one atom corresponds to 3 oscillators. Right? One atom is equivalent to 3 oscillators. And we're going to focus on oscillators. Not really atoms, oscillators. So then what you do is you go and you say, okay, let me remind myself what I know from quantum mechanics about a microscopic harmonic oscillator, specifically the energy levels. Okay? Because what I've got is a whole bunch of microscopic harmonic oscillators with natural frequency F. What are the possible energies that they could have? Right? So it's quantum mechanics. Okay? Any individual harmonic oscillator has discrete energy levels, right? That's certainly no surprise if we're talking about a quantum system and it's a bound system. These atoms are not free to roam around all over. They're bound to particular equilibrium sites. And so I expect the energy that these atoms could have to be discrete. Okay? And it's a very famous formula for the possible energies. It depends on a quantum number. And I'm going to use the symbol n for a quantum number. And the allowed energies are quantum number n plus a half times Planck's constant times the natural frequency of the oscillator, f. Where you discover from Schrodinger's equation that the allowed values for the quantum number n are any non-negative integer. 0 on up unending. Okay? So the little n here is what's called a quantum number. We've already said what f is. It's the natural frequency of each of the oscillators. Okay? And it's also helpful to draw an energy level diagram for a harmonic oscillator. I'll draw an axis here, a spatial axis. It could be x, it could be y, it could be z, whatever. And I'm going to draw an energy axis going upwards. Okay? I'm going to make the energy axis dimensionless by taking the energy and dividing it by hf. H times f, look at the formula, must have dimensions of energy. So I'm going to plot E divided by hf, so I have a dimensionless vertical axis. I'm also going to plot, on this picture, the parabolic potential energy function of the harmonic oscillator. 1/2 k times, if I think of this axis as x, right? 1/2 k sub s times x squared. Right? So that's the parabolic potential energy function. And then I list all the possible energies. But it's not continuous, it's discrete, where I can only put in here one of these allowed quantum numbers. The obviously smallest quantum number gives you what's called the ground state. That's a 0 here. So the energy is 1/2 hf. So on this scale, E over hf, I start at the tick mark 1/2. Put 1/2 here. And then let me draw, this is how most of the books draw it, a horizontal line going across, but terminating where I meet the graph of the potential energy function. That's meant to denote the fact that, at least classically, you can't go beyond, if you're in this particular state, those two extremes on the x-axis, right? Those are the classical turning points of the harmonic oscillator for that given energy. Of course, quantum mechanically, there's a small probability that you would find it even beyond those classical turning points, but that's why they draw a picture that way, to show you the classical turning points. This state then corresponds to the value for the quantum number n equals 0. The next possible energy level corresponds to taking the quantum number n equals 1 here. That's going to give me obviously 3/2 times hf. So I'm going to go up. That was a 1/2. About there. I'll be at 3/2. And I'll have a state going across like that. And that corresponds to n equals 1. Then if n is 2, I'll go up to, on this axis, 5/2. Notice the region of the x-axis that's available gets larger. N equals 2. You get the idea, right? Dot, dot, dot. Goes on up that way. Notice that, I can at least show it with these two, the spacing between adjacent energy levels stays the same as you go up on this diagram. The spacing between adjacent energy levels never changes. And the amount of energy of that spacing is h times f. Okay? So one of the key things about the energy level diagram of the harmonic oscillator is that the energy levels are equally spaced. That's the hallmark of the harmonic oscillator. There aren't any other systems out there that do that. Energy levels of a hydrogen atom are not equally spaced as you go up the energy axis. Okay? And you can talk about the quantum of energy for the oscillator is h times f, the amount of this jump between adjacent levels. That means h times f is a very important amount of energy for a harmonic oscillator. You give it that amount, it can go up one step in the diagram. Or it can give up that amount and go down one step. Okay? That being the case, we can think of, this is in fact what physicists do a lot, we're going to think of the value of the quantum number n as telling us how many energy quanta the oscillator has. We interpret the quantum number n as how many quanta of energy the oscillator contains. So if we're down here in the ground state, we'll say the oscillator has no quanta of energy. If we're in the first excited state, we'll say that the oscillator has one quantum of energy. There are no limits going up this way as to how many, in principle, how many quanta of energy an oscillator could have. Okay? But the lowest number is 0. Okay? All right. So, let's start talking about microstate and macrostate for lattice vibrations in a solid, this picture. Okay? So what are we going to take, what are we going to mean when we say microstate? What are we going to mean when we say macrostate? And how are we going to calculate the multiplicity of a macrostate? All right. So, 3. We'll take a toy model which consists of really the smallest number you could have, 3 oscillators. That'd be 1 atom. I guess you couldn't really call that a solid, but it's going to help us build up the ideas here. Okay? And let's say that this toy, this model, has 3 oscillators, and for these 3 oscillators we have Q quanta of energy that can be distributed amongst the oscillators. Q could be any non-negative integer, 0, 1, 2, 3. All right, I've got some number of energy quanta, that's Q. And I'm going to distribute those Q energy quanta amongst these 3 oscillators. Okay? So what are we going to mean by a microstate when we're talking about lattice vibrations in a solid? We mean a detailed partitioning of Q quanta among capital N oscillators. In our case, capital N is 3. And we're going to make a table showing you all the possible ways to partition Q quanta amongst N oscillators. Okay? What will we mean by a macrostate of lattice vibrations in a solid? Just the total energy of the N oscillators. I don't care all the details of, well, for that total energy, oscillator 1 has this much of it, oscillator 2 has this much of it, oscillator 3 has this much of it. In a macrostate, I don't want all that detail. Okay? Just tell me the total energy. So let's make a table, like I did for the 2-state paramagnet, so we can figure out how to calculate the multiplicity. Okay, so the first grouping here going down will be the partitioning in detail. So that's where I'm going to list the microstates. And to do that, what I'm going to have to do is I'm going to have to go down. I've got 3 oscillators only in this toy model, and I'm going to have to go down the line, thinking of the oscillators as entities, 1 oscillator at a time, and asking you, how many quanta do you have? How many do you have? How many do you have? It can answer me by just telling me the value of its own quantum number. I'm in state n equals 1. I'll say thank you, like a census. Got you recorded. Then I'll go down to the next oscillator. How many quanta do you have? I'm in quantum state n equals 0. Okay, thank you. Right? And so we're going to make a table. And the way we're going to write this partitioning in detail is we're going to denote, we're going to use quantum numbers. We'll label them little n1, little n2, little n3. We've got 3 oscillators. Each can have its own quantum number. Okay? That's part of this table. We're going to start working our way down. But then on next going over here, I'm also going to talk about specifying the total energy. You want to think of that as like E over HF. That's going to be a macro state, where I just specify the total energy. And then the last column way down here will be the multiplicity of a macro state. I said I have Q quanta of energy to distribute amongst these three N, capital N equals 3 oscillators. In order to see how the counting is going to go, we need to be more specific. So we got to take some example possible values for Q. Okay? Start simple and work your way up. The simplest scenario is that I have a total of 0 energy quanta to allocate. So I'll put over here Q equals 0 and give you a detailed partitioning, tell you exactly in detail what these 3 quantum numbers are. Well, there's not too much doubt as to what those have to be. They have to all 3 be 0. Total energy. Total energy, well, technically it's 1/2 HF for each one, right? But let's just say I'm going to ignore that lowest energy. You know what that's called in a harmonic oscillator? The lowest energy is called, it's called the ground state energy, but in a harmonic oscillator it also has a special name. It's called 0-point energy. Okay? Sometimes 0-point energy is important. For specifying a macro state, it is not. So I'm just going to say that total energy is 0. So we're ignoring the 0-point energy. In other words, I'm just shifting the 0 energy from the bottom of that well to there. Okay? All right. And then, of course, this is the only possible way to partition 0 energy quanta amongst 3 oscillators. So there is only one microstate corresponding to that macro state, so the multiplicity has to be 1. And that's an entry in our counting table. Now, we've got to go up from there. The next simplest scenario would be to have Q equals 1 quantum of energy to allocate amongst 3 oscillators. Now you've got to list all the possible ways to do that. Not hard, right? You've got 1 unit. Quantum mechanics says I can't subdivide that unit, right? I can't give 1/2 a quantum to one and 1.5 quantum to another, right? That's quantum mechanics. You cannot divide up the quanta into any smaller unit than h times f. So I can only give out in discrete units. So I could give the 1 unit to oscillator 1, in which I have to say, as Dr. McCulloch would say, tough noogies, to 2 and 3. You don't get any. Or I could give the 1 quantum of energy to oscillator 2 with nothing to the other 2. Or the 1 quantum of energy could go to oscillator 3. Those are 3 different detailed partitioning options you have, but they all correspond to an energy E over h bar of 1. So that is the macro state with energy E over hf equal to 1. Notice there are 3 microstates corresponding to that macro state, so the multiplicity is 3. Okay? We've got to do enough of these so we can see that we're going to get the multiplicity calculation correct. So now we'll allocate 2. Okay? Take 20 seconds and do it. Tell me what you get. How many specifically microstates? Notice that this will correspond. We will have a macro state with total energy E over hf equal to 2. How many microstates do you get? How many did you get? 6? 6? 6? Looks like 6. Because you could do something like this. All 2 to oscillator 1 and none to the others. Or you can give 2 oscillator units to oscillator, or 2 energy units to oscillator 2, or 2 energy units to oscillator 3. That's one possible way to to divide up the energy. The other possible way is do 1 and 1s, right? You can do 1, 1, 0, 1, 0, 1, 0, 1, 1. Now I don't think there are any other ways. So there are 6 distinct microstates, all corresponding to a macrostate with a total energy of 2HF. So the multiplicity is 6. Okay, tell me how many there are for 3. That's the last one we're going to do. You got to do enough that when you do your multiplicity equation, you can check it enough if you feel confident. Note that this macrostate will be a total energy of 3HF. How many you get? 10? 10. Okay? And you've made the table for yourself, right? So you know, for example, you could give all 3 quanta to the first oscillator, or all 3 to the second, or all 3 to the third, or you could do 2 and 1, or give each oscillator 1 quanta. Right? So you should find that there are 10 individual microstates corresponding to the macrostate with a total energy of 3HF. Okay? Alright, now, it gets pretty tedious to do it this way. We want a formula for that multiplicity column. Okay? So that if we can just calculate the multiplicity for what's called an Einstein solid. Somebody came up with a clever little trick for doing it. I don't know who did it. It may very well have been Feynman. But what we want next is the multiplicity formula for this Einstein model of lattice vibrations in a solid, which is called the Einstein solid. Okay? All right. So we're talking about N oscillators in general, and a total of Q energy quanta. Right? I want to know how many microstates are there? How many ways are there of divvying up the Q quanta amongst the N oscillators, right? How many microstates possible? I'm going to show you a clever little pictorial way of representing the microstates, and this pictorial way will help us figure out the multiplicity formula. I say that this might come from Feynman because he was big on pictures, okay, as ways of demonstrating what's going on physically. So in this pictorial method, what you do to represent a particular microstate is you use a dot to represent an energy quantum and a vertical line segment to draw a partition between oscillators. So for example, let's say I have 3 oscillators and 3 quanta of energy. One way to represent a microstate, I've got to divvy up the 3 quanta amongst the 3 oscillators, is to give one energy quantum to oscillator 1, then I'll go on to oscillator 2, I'll give it 2 energy quanta, then I'll go on to oscillator 3, and I have none left for that, so I leave it blank. Okay? So that I have a total, in this case, of 1, 2, 3, 4, 5 symbols. 3 dots and 2 partitions. Okay? So you will always have Q dots to represent the energy quanta, and n-1 lines to partition up your oscillators. Question?
No, I'm trying to guess the one.
Okay, that's fine, good. Okay? Okay? So my point is, you could do this. This would represent the case where this entry in the first column would be 1, the entry in this column would be 2, and the entry in this column would be 0. You can do this if you want to for fun. You could go down every one of these microstates, no matter where we are here, and you could draw the picture that goes with it. Okay? But here's why this is important, okay? Or useful. Every possible sequence of dots and lines represents a possible microstate. Right? It represents a microstate. It's a way in pictures to show you the detailed partitioning of the energy. So now I'm going to ask this question. How many ways, I'm going to ask the question twice. Here's the first way. How many ways to arrange Q dots and n-1 lines? Let me ask that a slightly different version of that question, which I think will be the question that will enable us to get what we want. Okay? So here's another question analogous to the first one. Of a total of how many symbols, I don't care whether it's a dot or a line, total do I have? Q plus n-1. Okay? So of a total of Q plus n-1 symbols, how many ways to pick Q dots? I've got this many total symbols. All symbols go into one of 2 categories, a dot or a line. This is how many total symbols there are. Out of that total, I've got to pick Q of them to be dots. How many ways are there to do it? Because that's the multiplicity, right? Do you have the formula? Okay, I'll call it in just a second. So, the answer to that question will be the multiplicity function. Remember, the symbol is capital Omega. There are 2 key things you have to tell me before I calculate the multiplicity of a macrostate in an Einstein solid. How many oscillators total are there? N. And how many quanta of energy total are there? Q. So what I've said is, that's the number way of choosing Q objects out of a total of Q plus n-1. That's what that notation means, right? Number of ways of choosing Q objects from Q plus n-1 total. Okay, so what's the formula?
It's the factorial of the top of Q plus n-1
Plus n-1, all that factorial.
over Q factorial, and then that minus Q.
And then the total minus Q factorial. But the total is Q plus n-1. So I take and I subtract q from that, and I'm left with n minus 1 factorial. Okay? Notice it's the same idea as the two-state paramagnet. In the two-state paramagnet, I mean, it looks a little different, but it's the same counting idea. It was the number way of choosing out of n dipoles total, some particular number of them to be dipole up. Right? And that was total number of dipoles factorial over number of dipoles up factorial times number of dipoles down factorial. It's the same basic idea. Okay? So that's what we're going to use, and we're going to use this a lot for the multiplicity when we're studying the Einstein solid. Now we've got two systems now, the two-state paramagnet and the Einstein solid, that we have multiplicity functions for. Okay? One more thing and then we'll take our break. Let's do our sanity check for this equation 1 to make sure that it gives those entries over there in the last column of our table. Okay? So step 5 will be a sanity check. We're going to compare equation 1 with our table. Starting at the top and going down for all the entries we have. So the top entry would be to calculate the multiplicity for 3 oscillators. So the capital N is 3. The top entry in the table corresponds to a total of 0 energy quanta. So Q equals 0. Okay, so I apply equation 1 with N equals 3 and Q equals 0. So what do I have in the numerator? 0 plus 3 minus 1, 2 factorial. Over 0 factorial for Q factorial, and 3 minus 1 is 2 factorial. So what is that? It's 1, right? 1. Well, that was our multiplicity for that particular macrostate. Let's do the next one. I'll go over here. So now we're talking about 3 oscillators and 1 quantum of energy. Now I'm talking about this entry, right here. Okay. So I have in the numerator, Q plus N minus 1. 1 plus 3 is 4, minus 1 is 3. So 3 factorial over 1 factorial, 2 factorial. Yes? Can you see what that's going to be? 3. Next one. Multiplicity for 3 oscillators and 2 energy quanta. So let's see. N minus 1 is 2. Q is 2. 2 plus 2 is 4. In the numerator I have 4 factorial over Q factorial, 2. And N minus 1, 2. Now, let's do this one carefully. 4 times 3 times 2 times 1 in the numerator. 2 times 1 times 2 times 1. In the denominator, there's a 2 times 1 and 2 times 1. That 1 is the denominator. Who cares? There's a 2 there. I can leave that there. Take that out of the 4. Looks like in the numerator, I'm left with a 3 times 2. And since we did the last one, we did one more, let's do that. 3 oscillators and 3 quanta. That's 5 factorial over 3 factorial, 2 factorial. That's 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 2 times 1. 2 times 1, 2 times 1. 3, 3, 2 out of the 4, leaving 2. The one downstairs, who cares? Looks like I have a 5 times 2 in the numerator, which is 10. Okay? Seems like we have got it. Okay, so now we have 2 systems and we know how to calculate the multiplicity of the macrostate for each. That's just getting us set up Now, after we'll take our break, and when we come back, we're going to start building our way towards the second law of thermodynamics.